So for today's lesson, we are going to kind of take a step back from, I guess, like the heavier trig stuff that we've been doing lately with the angles and the trig functions and stuff. And we are going to take a step back into our second favorite thing, because our first favorite thing in this class is factoring. And we are going to talk about logarithms. All right, because the last time we really talked about logarithms was the property of logarithms, and we talked about the common log and the natural log. All right, and you know what? Just for fun, I'm going to take a moment. We're going to do a little review in this box right here, okay? Because I feel like some of us have forgotten. All right, remember, logarithms are really just ways to write exponents. All right, that's where we get all those logarithmic properties, because they're very similar to exponential properties. All right, but the big thing is that logs have to have bases. All right, just like exponents have bases. Okay, and we talked about the common log, which we write with literally the word log. Okay, and that's what your calculator log button means. It's the common log. All right, and the common log is base 10. All right, the common log is base 10. So that means that 10 as a base for an exponential equation and a log undo each other. Okay, so that's like if I have something, we'll say, if I say the log of x is equal to 2, and I want to find x, since this is a common log, I can raise this whole side to the 10th power. Sorry, this was being a different color. And then the 10 and the common log cancel each other out, so I'm left with just x. And then I do it on this side, so it's going to be 10 to the 2nd power, which is 100. Okay? Apparently I need to extend my review box. Hold on. Alright, and then we also had this other thing, which was called the natural log. Okay, and that uses an L and an N, which is also a button on your calculator. And the reason we have a natural log is because that guy named Euler discovered this naturally occurring exponent. All right, so this natural log has a base of e. Just like the common log had a base 10. All right, every logarithm has to have an exponent that goes along with it because they're inverses of each other. Okay, and just like the 10 would undo the common log, the e will undo the natural log. All right, so if I had the natural log of x equal to 2, and I wanted to solve x, I could do e on both sides. I could read both sides by e, and then the e and the natural log will cancel each other out. But I got to do the same thing over here. So x is equal to e squared, and there's an e button in your calculator, and it's going to give you some decimal. All right. So remember, natural log and e cancel each other out. Base 10 and log cancel each other out. All right, and we could have done this the other way too. If instead of being told the natural log of x was being equal to something, I could have said e to the x is equal to 5. Well, how am I going to solve for x? I could take the natural log of both sides, because I know the natural log and e cancel each other out. So that means x is equal to the natural log of 5, which you will put in your button and you will get some some decimal. Same thing for the common log. All right, if I had 10 to the x is equal to 4, you can take the log of both sides, the common log, and I get that x is equal to whatever the log of 4 is. And you put that in your calculator and you get some decimal. So there's my mini logarithm review rant. Okay, now let's get back to the new stuff. I'll put a nice line down all this review. Boop, boop, boop. Okay. So, what are we going to do next? In my opinion, it's actually kind of cool what we're going to do next. Now we're going to use logarithms to solve exponential equations. Alright, so I don't even put the date on there because I don't know what day you guys are going to watch this. All right, so using logarithms to solve exponential equations. What do I mean by exponential equations? These are those things that you guys hate doing. Alright, this is where I give you a question and I say, well, solve for x, obviously. And I give you 4 to the x is equal to 8. And this is when you have to change the base of both sides so we can set the exponents equal to each other. So you say, okay, well, 4 can really be written as 2 squared raised to the x power. And that's nice because 8 can also be written with a base of 2 because that's 2 to the 3rd power. And this left side, you multiply the exponent. So this is really 2 to the 2x is equal to 2 cubed. And now since our bases are the same, we can set our exponents equal to each other, and you get that x is equal to 3/2. Okay? And so that's great because it's, it was pretty easy to see that 4 and 8 could both be written as 2 raised to some power. And sometimes it takes a little bit of work messing with your calculator. If they give you something like 243 or whatever, you got to mess with your calculator and say, okay, if I do 2 to the 4th, do I get that? If I do 2 to the 5th, do I get that? What if I do 3 to the 4th? So it takes a little bit of legwork. But now we are going to be able to solve these equations even if we cannot somehow write those things to have the same base. All right? For example, what if I give you 3 to the x power is equal to 5. And I wanted you to solve for x. So far, we have no way to solve this, all right? 3 is prime. There's no way to write that as something raised to a power. The same with 5. 5 is prime. We cannot somehow write 5 as some other thing raised to a power. So what we are going to do is we are going to use logarithms to our advantage, all right? Because if I look, what I'm solving for is in my exponent. Right? I want x and x is in my exponent. And we know with logarithms that if you take the log of something with an exponent, that exponent pops out in front. All right? So if I take the log of both sides, because it's an equation, so we have to do it to both sides. Now we use that property of logarithms, we take that exponent right here and we pop it out in front. So this is going to become x times the log of 3 equal to the log of 5. And now, since we have x times the log of 3, I just divide both sides by the log of 3. Those cancel, and I get x is equal to the log of 5 divided by the log of 3. Which, I don't know what the log of 5 is or the log of 3 is, but that's why we give you guys calculators. Log of 5 divided by log of 3. You get that x is approximately 1.46. There is your answer. Okay, so now we can find answers even if we cannot change our bases. And we can do that using this cool property of logarithms. All right, let's do another example. All right, we're only going to do a couple of these because I think you guys should hopefully already see the gist. Okay, so next one, we're still going to solve for x. Nine to the x is equal to 14. Okay, now in this case, 9 and 14 are not prime, but there is still no way to write 9 as something raised to some power and 14 to have that same base raised to a power. So we can't do what we've been doing. So instead, let's take the log of both sides, because the logarithm will take this exponent and pop it out. So I'll take the log of that side, and I'll take the log of this side. It's an equation. You have to do it to both sides. So I have the log of 9 to the x power is equal to the log of 14. Properties of exponent, or properties of logarithms, you can take the exponent, you can pop it out. So this is equivalent to x times the log of 9, which is equal to the log of 14. Want to get x by itself, divide both sides by the log of 9. These cancel, I get x is equal to the log of 14 divided by the log of 9, which you punch into your handy dandy TI 83 or 84, which I'm doing right now. And you get that x is approximately 1.2. Boom, big. Okay, I'm going to do one more example and then I'm done. How am I doing on time? Oh, bueno, bueno. One more example. And I'll actually put in round to the nearest 10. Because you're always going to get some crazy decimal with these, so you need to pay attention to what the directions tell you to round to. Okay, I'm going to do 12 times, why did that do that? 12, why did that do that again? Maybe third time's the charm. 12 times, there we go, 12 to the x power, which is equal to 500. All right, there are actually a couple of different ways to do this problem. I'm going to do them all, just so you guys can see that there is, in fact, more than one way to think through a math problem. All right, we could do what we've been doing, which is automatically taking the log of both sides. Totally cool. Log of the left, log of the right. So this is the log of 12 times 12 to the x power, which is equal to the log of 500. Properties of logarithms: if you have multiplication inside of a log, that changes to addition. So this is really the log of 12 plus the log of 12 to the x. Put those in parentheses. Which is equal to the log of 500. This one over here on the left doesn't have an x in it, so I'll subtract it and move it over. So this is the log of 500 minus the log of 12. Now, I can take that x, because it's in the exponent, and I'll pop it out in front. So this is x times the log of 12. And now I can divide everything by the log of 12. So I can get x by itself. And so I get that x is equal to the log of 500 minus the log of 12. And all of that is divided by the log of 12. And you put that in your calculator, you round, it's about 1.5. Alright, so that is one way to do this problem. Another way to do this problem, I'll do that over here. All right, we started off with 12 times 12 to the x equals 500. Some of you might have looked at this and said that first 12 doesn't even have an x in it, so I'm just going to move it over to begin with. Divide both sides by 12. So now you have that 12 to the x is equal to 500 over 12. But now we still have that x in our exponent, so now we're going to have to take the log of both sides. And notice we have logarithmic properties rocking on both sides of this equation now. All right, in the left side, we have that exponent that we can pop out. So this is going to become x times the log of 12. And then on the right, we have division. And anytime we have division inside of a logarithm, that changes to subtraction. So this is going to be equal to the log of 500 minus the log of 12. And then, last but not least, to get x by itself, we divide both sides by the log of 12. And we get that x is equal to the log of 500 minus the log of 12 all over the log of 12. Which is identical to what I got the first way that I solved this problem. Alright, here was my first answer. Here's my second answer. The exact same thing. So we're still going to get about 1.5 after we pop that in and round it. Okay? I'm going to do the other way, just because I think it's kind of cool. Okay? I'll extend my page. Let's do method number 3. I started off with a 12 times 12 to the x is equal to 500. Some of you might be thinking to yourselves, those have the same base. So I can combine those because this is really 12 to the first power. So this whole thing on the left-hand side is really 12 to the 1 plus x power, or x plus 1. Because when things have the same base, you add the exponents when you're multiplying. All right? But now we have a variable in the exponent, so we have to use logarithms. All right? 12 and 500 don't have a common base. So let's take the log of both sides. So this is the log of 12 to the 1 plus x, which is equal to the log of 500. We have that exponent, so we can pop that out in front. So this is going to be 1 plus x times the log of 12, which is equal to the log of 500. And since this thing is in parentheses out here, it's being multiplied by this log 12, we would have to distribute. So really we get the log of 12 plus x times the log of 12, which is equal to the log of 500. And then we're going to subtract this log 12 over. So I get x times the log of 12, which is equal to the log of 500 minus log 12. And divide both sides by log 12. And that's really x is equal to the log of 500 minus the log of 12 all over the log of 12, which should look really familiar because that's what I got the other 2 times. All right, 3 different ways to do the exact same problem. I don't care which way you do it. All I care is that you do it right, and that when you pop this in your calculator, you round appropriately, and you get that x is approximately 1.5. Okay? So let's go to another page. Let's do a mini recap. From my little review in the beginning, we have that common logs. and base 10 go together. They are in fact inverses of each other. The same thing with natural logs. And base E. Alright, these are inverses. 10 and common logs are inverses. E and the natural log are inverses. That's why they're the same button on your calculator. So there was that. We also have that now we can use logarithms to solve exponential equations. Specifically, we want to use them when we cannot get our exponential equations to have the same base. All right? So definitely use when we can't get the same base. So this is really handy if you guys are bad at identifying how to write two things with the same base. All right? If you can't do it, use logarithms, as long as the directions don't tell you to explicitly do it without logarithms. All right, so this is a really nice tool. And I do want to point out that even though I did all of these examples using log, the common log, I could have done it using natural log. Okay. And that is that. I am Dunzo. Don't forget to take the quiz afterwards. Adios.